Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled Soldering. Soldering is a process of joining two metal surfaces together using a filler metal called solder. The soldering process involves heating the surfaces to be joined and melting the solder, which is then allowed to cool and solidify, creating a strong and durable joint. Soldering is commonly used in the electronics industry for the manufacture and repair of printed circuit boards, PCBs, and other electronic components. It is also used in plumbing and metalwork, as well as in the manufacture of jewelry and other decorative items. The solder used in the process can vary in composition, with different alloys used for different applications. Common solder alloys include tin lead, tin silver, and tin copper, among others. Lead-free solder has also become more widely used in recent years due to health and environmental concerns associated with the use of lead. In addition to the type of solder used, the temperature and method of heating also play a crucial role in the soldering process. Different types of solder require different temperatures to melt, and heating must be carefully controlled to avoid damaging the materials being joined or creating weak joints. There are several methods of heating used in soldering, including soldering irons, torches, and hot air guns. Each method has its own advantages and disadvantages, and the choice of method depends on the application and the materials being joined. Soldering is an important skill for many industries and hobbies, and it requires a combination of technical knowledge and practical experience to achieve good results. There is evidence that soldering was employed as early as 5,000 years ago in Mesopotamia. Soldering and brazing are thought to have originated very early in the history of metalworking, probably before 4000 BC. Sumerian swords from circa 3000 BC were assembled using hard soldering. Soldering was historically used to make jewelry, cookware, and cooking tools, assembling stained glass, as well as other uses. Soldering is used in plumbing, electronics, and metalwork, from flashing to jewelry and musical instruments. Soldering provides reasonably permanent but reversible connections between copper pipes and plumbing systems, as well as joints in sheet metal objects such as food cans, roof flashing, rain gutters, and automobile radiators. Jewelry components, machine tools, and some refrigeration and plumbing components are often assembled and repaired by the higher temperature silver soldering process. Small mechanical parts are often soldered or brazed as well. Soldering is also used to join lead came and copper foil in stained glass work. Electronic soldering connects electronical wiring to devices and electronic components to printed circuit boards. Electronic connections may be hand soldered with a soldering iron. Automated methods such as wave soldering or use of ovens can make many joints on a complex circuit board in one operation, vastly reducing production cost of electronic devices. Musical instruments, especially brass and woodwind instruments, use a combination of soldering and brazing in their assembly. Brass bodies are often soldered together, while keywork and braces are most often brazed. The solderability of a substrate is a measure of the ease with which a soldered joint can be made to that material. Some metals are easier to solder than others. Copper, zinc, brass, silver, and gold are easy. Iron, mild steel, and nickel are next in difficulty. Because of their thin, strong oxide films, stainless steel and some aluminum alloys are even more difficult to solder. Titanium, magnesium, cast irons, some high-carbon steels, ceramics, and graphite can be soldered, but it involves a process similar to joining carbides. They are first plated with a suitable metallic element that includes interfacial bonding. Soldering filler materials are available in many different alloys for different applications. In electronics assembly, the eutectic alloy with 63% tin and 37% lead, or 60/40, which is almost identical in melting point, has been the alloy of choice. Other alloys are used for plumbing, mechanical assembly, and other applications. Some examples of soft soldered are tin lead for general purposes, tin zinc for joining aluminum, lead silver for strength at higher than room temperature, cadmium silver for strength at high temperatures, zinc aluminum for aluminum and corrosion resistance, and tin silver and tin bismuth for electronics. A eutectic formulation has advantages when applied to soldering. The liquidus and solidus temperatures are the same, so there is no plastic phase, and it has the lowest possible melting point. Having the lowest possible melting point minimizes heat stress on electronic components during soldering, and having no plastic phase allows for quicker wetting as the solder heats up, and quicker setup as the solder cools. A non-eutectic formulation must remain still as the temperature drops through the liquidus and solidus temperatures. Any movement during the plastic phase may result in cracks, resulting in an unreliable joint. Common solder formulations based on tin and lead are listed below. The fraction represents percentage of tin first, then lead, totaling 100%. 6337 melts at 183 degrees Celsius, eutectic, the only mixture that melts at a point instead of over a range. 6040 melts between 183 to 190 degrees Celsius. 5050 melts between 183 to 215 degrees Celsius. For environmental reasons and the introduction of regulations such as the European RoHS, Restriction of Hazardous Substances Directive, lead-free solders are becoming more widely used. They are also suggested anywhere young children may come in contact with or for outdoor uses where rain and other precipitation may wash the lead into the groundwater. Unfortunately, common lead-free solders are not eutectic formulations, melting at around 220 degrees Celsius, making it more difficult to create reliable joints with them. Other common solders include low-temperature formulations, often containing bismuth, which are often used in join previously soldered assemblies without unsoldering earlier connections, and high-temperature formulations, usually containing silver, which are used for high-temperature operations or for first assembly of items which must not become unsoldered during subsequent operations. Alloying silver with other metals changes the melting point, adhesion and wetting characteristics, and tensile strength. Of all the brazing alloys, silver solders have the greatest strength and the broadest applications. Specialty alloys are available with properties such as higher strength, the ability to solder aluminum, better electrical conductivity, and higher corrosion resistance. There are three forms of soldering, each requiring progressively higher temperatures and producing an increasingly stronger joint strength. 1. Soft soldering, which originally used in tin lead alloy as the filler metal. 2. Silver soldering, which uses an alloy containing silver. 3. Brazing, which uses a brass alloy for the filler. The alloy of the filler metal for each type of soldering can be adjusted to modify the melting temperature of the filler. Soldering differs from gluing significantly in that the filler metals directly bond with the surfaces of the workpieces at the junction to form a bond that is both electrically conductive and gas and liquid tight. Soft soldering is characterized by having a melting point of the filler metal below approximately 400 degrees Celsius, whereas silver soldering and brazing use higher temperatures, typically requiring a flame or carbon arc torch to achieve the melting of the filler. Softer solder filler metals are typically alloys, often containing lead, that have liquidus temperatures below 350 degrees Celsius. In this soldering process, heat is applied to the parts to be joined, causing the solder to melt and to bond to the workpieces in a surface alloying process called wetting. In stranded wire, the solder is drawn up into the wire between the strands by capillary action in a process called wicking. Capillary action also takes place when the workpieces are very close together or touching. The joint's tensile strength is dependent on the filler metal used. In electrical soldering, little tensile strength comes from the added solder, which is why it is advised that wires be twisted or folded together before soldering to provide some mechanical strength for a joint. A good solder joint produces an electrically conductive water and gas tight joint. Each type of solder offers advantages and disadvantages. Soft solder is so called because of the soft lead that is its primary ingredient. Soft soldering uses the lowest temperatures, and so thermally stresses components the least, but does not make a strong joint and is unsuitable for mechanical load-bearing applications. It is also unsuitable for high-temperature applications as it loses strength and eventually melts. Silver soldering, as used by jewelers, machinists, and in some plumbing applications, requires the use of a torch or other high-temperature source and is much stronger than soft soldering. Brazing provides the strongest of the non-welded joints, but also requires the hottest temperatures to melt the filler metal, requiring a torch or other high-temperature source and darkened goggles to protect the eyes from the bright light produced by the white-hot work. It is often used to repair cast iron objects, wrought iron furniture, etc. Soldering operations can be performed with hand tools, one joint at a time, or en masse on a production line. Hand soldering is typically performed with the soldering iron, soldering gun, or a torch, or occasionally a hot air pencil. Sheet metal work was traditionally done with soldering coppers directly heated by a flame, with sufficient stored heat in the mass of the soldering copper to complete a joint. Gas torches, e.g. butane or propane, or electrically heated soldering irons are more convenient. All soldered joints require the same elements of cleaning of the metal parts to be joined, fitting up the joint, heating the parts, applying flux, applying the filler, removing heat, and holding the assembly still until the filler metal has completely solidified. Depending on the nature of flux material used and the application, cleaning of the joint may be required after it is cooled. Each solder alloy has characteristics that work best for certain applications, notably strength and conductivity, and each type of solder and alloy has different metalling temperatures. The term silver solder denotes the type of solder that is used. Some soft solders are silver-bearing alloys, used to solder silver-plated items. Lead-based solders should not be used on precious metals because the lead dissolves the metal and disfigures it. The distinction between soldering and brazing is based on the metalling temperature of the filler alloy. A temperature of 450 degrees Celsius is usually used as a practical demarcation between soldering and brazing. Soft soldering can be done with a heated iron, whereas the other methods typically require a higher temperature torch or a furnace to melt the filler metal. Different equipment is usually required since a soldering iron cannot achieve high enough temperatures for hard soldering or brazing. Brazing filler metal is stronger than silver solder, which is stronger than lead-based soft solder. Brazing solders are formulated primarily for strength. Silver solder is used by jewelers to protect the precious metal and by machinists and refrigeration technicians for its tensile strength, but lower melting temperature than brazing. And the primary benefit of soft solder is the low temperature used to prevent heat damage to electronic components and insulation. Since the joint is produced using a metal with a lower melting point than the workpiece, the joint will weaken as the ambient temperature approaches the melting point of the filler metal. For that reason, the higher temperature processes produce joints which are effective at higher temperatures. Brazed connections can be as strong or nearly as strong as the parts they connect, even at elevated temperatures. Hard soldering, or silver soldering, is used to join precious and semi-precious metals, such as gold, silver, brass, and copper. The solder is usually described as easy, medium, or hard in reference to its melting temperature, not the strength of the joint. Extra easy solder contains 56% silver and has a melting point of 618 degrees Celsius. Extra hard solder has 80% silver and melts at 740 degrees Celsius. If multiple joints are needed, then the jeweler will start with hard or extra hard solder and switch to lower temperature solders for later joints. Silver solder is somewhat absorbed by the surrounding metal, resulting in a joint that is actually stronger than the metal being joined. The metal being joined must be perfectly flush, as silver solder cannot normally be used as a filler and will not fill gaps. Another difference between brazing and soldering is how the solder is applied. In brazing, one generally uses rods that are touched to the joint while being heated. With silver soldering, small pieces of solder wire are placed onto the metal prior to heating. A flux, often made of boric acid and denatured alcohol, is used to keep the metal and solder clean and to prevent the solder from moving before it melts. When silver solder melts, it tends to flow towards the area of greatest heat. Jewelers can somewhat control the direction the solder moves by leading it with a torch. It will even sometimes run straight up along a seam. A number of solder materials, primarily zinc alloys, are used for soldering aluminum metal and alloys, and to a lesser extent, steel and zinc. This mechanical soldering is similar to a low-temperature brazing operation, in that the mechanical characteristics of the joint are reasonably good, and it can be used for structural repairs of those materials. The American Welding Society defines brazing as using filler metals with melting points over 450 degrees Celsius, or by traditional definition in the United States, above 800 degrees Fahrenheit. Aluminum soldering alloys generally have melting temperatures around 730 degrees Fahrenheit. This soldering brazing operation can use a propane torch heat source. These materials are often advertised as aluminum welding, but the process does not involve melting the base metal and therefore is not properly a weld. United States Military Standard, or mil-spec, specification MIL R4208 defines one standard for these zinc-based brazing soldering alloys. A number of products meet this specification or very similar performance standards. The purpose of flux is to facilitate the soldering process. One of the obstacles to a successful solder joint is an impurity at the site of the joint. For example, dirt, oil, or oxidation. The impurities can be removed by mechanical cleaning or by chemical means. But the elevated temperatures required to melt the filler metal, the solder, encourages the workpiece and the solder to reoxidize. This effect is accelerated as the soldering temperatures increase and can completely prevent the solder from joining to the workpiece. One of the earliest forms of flux was charcoal, which acts as a reducing agent and helps prevent oxidation during the soldering process. Some fluxes go beyond the simple prevention of oxidation and also provide some form of chemical cleaning, corrosion. Many fluxes also act as a wetting agent in the soldering process, reducing the surface tension of the molten solder and causing it to flow and wet the workpiece more easily. For many years, the most common type of flux used in electronics, soft soldering, was rosin-based, using the rosin from selected pine trees. It was nearly ideal in that it was non-corrosive and non-conductive at normal temperatures, but became mildly reactive or corrosive at elevated soldering temperatures. Plumbing and automotive applications, among others, typically use an acid-based hydrochloric acid flux, which provides rather aggressive cleaning of the joint. These fluxes cannot be used in electronics because their residues are conductive, leading to unintended electrical connections, and because they will eventually dissolve small diameter wires. Citric acid is an excellent water-soluble acid-type flux for copper and electronics, but must be washed off afterwards. Fluxes for soft solders are currently available in three basic formulations: water-soluble fluxes, higher activity fluxes which can be removed with water after soldering, no VOCs required for removal, no clean fluxes, mild enough to not require removal due to their non-conductive and non-corrosive residues. These fluxes are called no clean because the residue left after the solder operation is non-conductive and will not cause electrical shorts. Nevertheless, they leave a plainly visible white residue. No clean flux residue is acceptable on all three classes of PCBs as defined by IPC 610, provided it does not inhibit visual inspection, access to test points, or have a wet, tacky, or excessive residue that may spread onto other areas. Connector mating surfaces must also be free of flux residue. Fingerprints and no clean residue are a Class 3 defect. Traditional rosin fluxes, available in non-activated R, mildly activated RMA, and activated RA formulations. RA and RMA fluxes contain rosin combined with an activating agent, typically an acid, which increases the wettability of metals to which it is applied by removing existing oxides. The residue resulting from the use of RA flux is corrosive and must be cleaned. RMA flux is formulated to result in a residue which is less corrosive, so that cleaning becomes optional, though usually preferred. R flux is still less active and even less corrosive. Flux performance must be carefully evaluated for best results. A very mild no-clean flux might be perfectly acceptable for production equipment, but not give adequate performance for more variable hand soldering operations. Different types of soldering tools are made for specific applications. The required heat can be generated from burning fuel or from an electrically operated heating element, or by passing an electric current through the item to be soldered. Another method for soldering is to place solder and flux at the locations of joints in the object to be soldered. Then heat the entire object in an oven to melt the solder. Toaster ovens and handheld infrared lights have been used by hobbyists to replicate production soldering processes on a much smaller scale. A third method of soldering is to use a solder pot, where the part with flux is dipped in a small heated iron cup of liquid solder, or a pump in a bath of liquid solder produces an elevated wave of solder, which the part is quickly passed through. Wave soldering uses surface tension to keep solder from bridging the insulated gaps between the copper lines of flux-coated printed wiring boards, printed circuit boards. The electric soldering iron is widely used for hand soldering, consisting of a heating element in contact with the iron, a large mass of metal, usually copper, which is in contact with the working tip made of copper. Usually, soldering irons can be fitted with a variety of tips, ranging from blunt to very fine to chisel heads for hot cutting plastics rather than soldering. Plain copper tips are subject to erosion, dissolution, and hot solder, and may be plated with pure iron to prevent that. The simplest irons do not have temperature regulation. Small irons rapidly cool when used to solder to, say, a metal chassis, while large irons have tips too cumbersome for working on printed circuit boards, PCBs, and similar fine work. A 25-watt iron will not provide enough heat for large electrical connectors, joining copper roof flashings, or large stained glass lead came. On the other hand, a 100-watt iron may provide too much heat for PCBs. Temperature-controlled irons have a reserve of power and can maintain temperature over a wide range of work. A soldering gun heats a small cross-section copper tip very quickly by conducting a large AC current through it, using a large cross-section one-turn transformer. The copper tip then conducts the heat to the part like other soldering irons. A soldering gun will be larger and heavier than a heating element soldering iron of the same power rating because of the built-in transformer. Gas-powered irons using a catalytic tip to heat a bit without flame are used for portable applications. Hot air guns and pencils allow rework of component packages, such as surface mount devices, which cannot easily be performed with electric irons and guns. For non-electric applications, soldering torches can use a flame rather than a soldering tip to heat solder. Soldering torches are often powered by butane and are available in sizes ranging from very small butane oxygen units suitable for very fine but high-temperature jewelry work to full-size oxy-fuel torches suitable for much larger work, such as copper piping. Common multi-purpose propane torches, the same kind used for heat stripping paint and thawing pipes, can be used for soldering pipes and other fairly large objects, either with or without a soldering tip attachment. Pipes are generally soldered with a torch by directly applying the open flame. A soldering copper is a tool with a large copper head and a long handle, which is heated with a small direct flame and used to apply heat to sheet metal, such as tin-plated steel, for soldering. Typical soldering coppers have heads weighing between 1 and 4 pounds. The head provides a large thermal mass to store enough heat for soldering large areas before needing reheating in the fire. The larger the head, the longer the working time. The copper surface of the tool must be constantly cleaned and retinned during use. Historically, soldering coppers were standard tools used in auto bodywork, although body solder has been mostly superseded by spot welding for mechanical connection and non-metallic fillers for contouring. During World War II and for some time afterwards, SOE forces used small pyrotechnic self-soldering joints to make connections for the remote detonation of demolition and sabotage explosives. These consisted of a small copper tube partially filled with solder and a slow-burning pyrotechnic composition wrapped around the tube. The wires to be joined would be inserted into the tube, and a small blob of ignition compound allowed the device to be struck like a match to ignite the pyrotechnic and heat the tube for long enough to melt the solder and make the joint. Laser soldering is a technique where a 30 to 50 watt laser is used to melt and solder an electrical connection joint. Diode laser systems based on semiconductor junctions are used for this purpose. Suzanne Genicius patented laser soldering in 1980. Wavelengths are typically 808 nanometers through 980 nanometers. The beam is delivered via an optical fiber to the workpiece, with fiber diameters 800 micrometers and smaller. Since the beam out of the end of the fiber diverges rapidly, lenses are used to create a suitable spot size on the workpiece at a suitable working distance. A wire feeder is used to supply solder. Both lead tin and silver tin material can be soldered. Process recipes will differ depending on the alloy composition. For soldering 44-pin chip carriers to a board using soldering preforms, power levels were on the order of 10 watts and solder times approximately 1 second. Low power levels can lead to incomplete wetting and the formation of voids, both of which can weaken the joint. Photonic soldering is a relatively new process that uses broadband light from rapidly pulsing flash lamps to solder components to a circuit board. Energy consumption is approximately 85% less than that of a reflow oven, while the throughput is higher and the footprint is smaller. It is similar to photonic curing in that the components to be soldered are heated while the substrate remains relatively cool. This enables the use of high-temperature solders, such as SAC 305, even on thermally fragile substrates such as PET, cellulose, and fabrics. An entire circuit board can be processed in a few seconds. In some cases, masks are used, but it can also be performed without registration, enabling very high processing rates. Induction soldering uses induction heating by high-frequency alternating current in a surrounding copper coil. This induces currents in the part being soldered, which generates heat because of the higher resistance of a joint versus its surrounding metal, resistive heating. These copper coils can be shaped to fit the joint more precisely. A filler metal solder is placed between the facing surfaces, and this solder melts at a fairly low temperature. Fluxes are commonly used in induction soldering. This technique is particularly suited to continuously soldering, in which case these coils wrap around a cylinder or a pipe that needs to be soldered. Fiber focus infrared soldering is a technique where many infrared sources are led through fibers, then focused onto a single spot at which the connection is soldered. Resistance soldering is soldering in which the heat required to melt the solder is created by passing an electric current through the parts to be soldered. When electric current is conducted through any metal, heat is generated. When that current is confined to a smaller cross-sectional area, the heat produced in the entire circuit is concentrated in the portion with the reduced cross-sectional area. The current doing the heating is applied by electrodes or tips energized from a low open circuit voltage source, typically 2 to 7 volts. They can be tweezer-like for general connections or specially shaped to make contact with parts located closely together. Resistance soldering is unlike using a conduction iron, where heat is produced within an element and then passed through a thermally conductive tip into the joint area. A cold soldering iron requires time to reach working temperature and must be kept hot between solder joints. Thermal transfer may be inhibited if the tip is not kept properly wetted during use. With resistance soldering, an intense heat can be rapidly developed directly within the joint area and in a tightly controlled manner. This allows a faster ramp-up to the required solder melt temperature and minimizes thermal travel away from the solder joint, which helps to minimize the potential for thermal damage to materials or components in the surrounding area. Heat is only produced while each joint is being made, making resistance soldering more energy efficient. Because of these advantages, resistance soldering is common in industries which solder in small spaces, such as connectors and wire terminals, and where high power is required, such as desoldering automotive parts. Resistance soldering equipment, unlike conduction irons, can be used for difficult soldering and brazing applications where significantly higher temperatures may be required. This makes resistance comparable to flame soldering in some situations, but the resistance heat is more localized because of direct contact, whereas the flame might heat a larger area. Fluxless soldering with aid of conventional soldering iron, ultrasonic soldering iron, or specialized solder pot, an active solder that contains an active element, most often titanium, zirconium, or chromium. The active elements, owing to mechanical activation, react with the surface of the materials generally considered difficult to solder without pre-metallization. The active solders can be protected against excessive oxidation of their active element by addition of rare earth metals with higher affinity to oxygen. Another common additive is gallium, usually introduced as a wetting promoter. Mechanical activation needed for active soldering can be performed by brushing, for example, with use of stainless wire brush or steel spatula, or ultrasonic vibration. Active soldering has been shown to effectively bond ceramics, aluminum, titanium, silicon, graphite, and carbon nanotube-based structures at temperatures lower than 450 degrees Celsius, or use of protective atmosphere. Copper pipe or tube is commonly joined by soldering. When applied in a plumbing trade context in the United States, soldering is often referred to as sweating, and a tubing connection so made is referred to as a sweated joint. Outside the United States, sweating refers to the joining of flat metallic surfaces by a two-step process by which solder is first applied to one surface, then the first piece is placed in position against the second surface, and both are reheated to achieve the desired joint. Copper tubing conducts heat away much faster than a conventional handheld soldering iron or gun can provide, so a propane torch is most commonly used to deliver the necessary power. For large tubing sizes and fittings, a MAP-fueled, acetylene-fueled, or propylene-fueled torch is used with atmospheric air as the oxidizer. MAP oxygen or acetylene oxygen are rarely used because the flame temperature is much higher than the melting point of copper. Too much heat destroys the temper of hard-tempered copper tubing and can burn the flux out of a joint before the solder is added, resulting in a faulty joint. For larger tubing sizes, a torch fitted with various sizes of interchangeable swirl tips is employed to deliver the needed heating power. In the hands of a skilled tradesman, the hotter flame of acetylene, MAP, or propylene allows more joints to be completed per hour without damage to copper tempering. However, it is possible to use an electrical tool to solder joints in copper pipe sized from 8 to 22 millimeters. For example, the Antex Pipe Master is recommended for use in tight spaces when open flames are hazardous or by do-it-yourself users. The pliers-like tool uses heated fitted jaws that completely encircle the pipe, allowing a joint to be melted in as little as 10 seconds. Solder fittings, also known as capillary fittings, are usually used for copper joints. These fittings are short sections of smooth pipe designed to slide over the outside of the mating tube. Commonly used fittings include for straight connectors, reducers, bends, and tees. There are two types of solder fittings: end feed fittings, which contain no solder, and solder ring fittings, also known as Yorkshire fittings, in which there is a ring of solder in a small circular recess inside the fitting. As with all solder joints, all parts to be joined must be clean and oxide free. Internal and external wire brushes are available for the common pipe and fitting sizes. Emery cloth and wire wool are frequently used as well, although metal wool products are discouraged, as they can contain oil which would contaminate the joint. Because of the size of the parts involved and the high activity and contaminating tendency of the flame, plumbing fluxes are typically much more chemically active and often more acidic than electronic fluxes. Because plumbing joints may be done at an angle, even upside down, plumbing fluxes are generally formulated as pastes, which stay in place better than liquids. Flux is applied to all surfaces of the joint, inside and out. Flux residues are removed after the joint is complete to prevent erosion and failure of the joint. Many plumbing solder formulations are available, with different characteristics such as higher or lower melting temperature, depending on the specific requirements of the job. Building codes currently almost universally require the use of lead-free solder for drinking water piping, and also flux must be approved for drinking water applications, though traditional tin lead solder is still available. Studies have shown that lead soldered plumbing pipes can result in elevated levels of lead in drinking water. Since copper pipe quickly conducts heat away from a joint, great care must be taken to ensure that the joint is properly heated through to obtain a good bond. After the joint is properly cleaned, fluxed, and fitted, the torch flame is applied to the thickest part of the joint, typically the fitting within the pipe inside it, with the solder applied at the gap between the tube and the fitting. When all the parts are heated through, the solder will melt and flow into the joint by capillary action. The torch may need to be moved around the joint to ensure all areas are wetted out. However, the installer must take care to not overheat the areas being soldered. If the tube begins to discolor, it means that the tube has been overheated and is beginning to oxidize, stopping the flow of the solder and causing the soldered joint not to seal properly. Before oxidation, the molten solder will follow the heat of the torch around the joint. When the joint is properly wetted out, the solder and then the heat are removed. And while the joint is still very hot, it is usually wiped with a dry rag. This removes excess solder as well as flux residue before it cools down and hardens. With a solder ring joint, the joint is heated until a ring of molten solder is visible around the edge of the fitting and allowed to cool. Of the three methods of connecting copper tubing, solder connections require the most skill, but soldering copper is a very reliable process, provided some basic conditions are met. The tubing and fittings must be cleaned to bare metal with no tarnish. Any pressure which is formed by heating of the tubing must have an outlet. The joint must be dry, which can be challenging when repairing water pipes. Copper is only one material that is joined in this manner. Brass fittings are often used for valves or as a connection fitting between copper and other metals. Brass piping is soldered in this manner in the making of brass instruments and some woodwind, saxophone, and flute musical instruments. Wire brush, wire wool, and emery cloth are commonly used to prepare plumbing joints for connection. Bristle brushes are usually used to apply plumbing paste flux. A heavy rag is usually used to remove flux from a plumbing joint before it cools and hardens. A fiberglass brush can also be used. When soldering pipes closely connected to valves, such as in refrigeration systems, it may be necessary to protect the valve from heat that could damage rubber or plastic components within. In this case, a wet cloth wrapped around the valve can often sink sufficient heat through the boiling of the water to protect the valve. In the joining of copper tube, failure to properly heat and fill a joint may lead to a void being formed. This is usually a result of improper placement of a flame. If the heat of the flame is not directed at the back of the fitting cup and the solder wire applied degrees opposite the flame, then solder will quickly fill the opening of the fitting, trapping some flux inside the joint. This bubble of trapped flux is the void, an area inside a solder joint where the solder is unable to completely fill the fitting's cup because flux has become sealed inside the joint, preventing solder from occupying that space. Historically, stained glass soldering tips were copper, heated by being placed in a charcoal burning brazier. Multiple tips were used. When one tip cooled down from use, it was placed back in the brazier of charcoal, and the next tip was used. More recently, electrically heated soldering irons are used. These are heated by a coil or ceramic heating element inside the tip of the iron. Different power ratings are available, and temperature can be controlled electronically. These characteristics allow longer beads to be run without interrupting the work to change tips. Soldering irons designed for electronic use are often effective, though they are sometimes underpowered for the heavy copper and lead came used in stained glass work. Oleic acid is a classic flux material that has been used to improve solderability. Tiffany-type stained glass is made by gluing copper foil around the edges of the pieces of glass and then soldering them together. This method makes it possible to create three-dimensional stained glass pieces.